4.8, Antiderivatives. So this comic here is one that you're not going to get until the end of this lesson. But funny story, one of my former students actually made me a +C stamp. And so at the end of this lesson, come back to this comic and see if you can figure out why the creator of this comic may have made this.
A function, capital F, is called an antiderivative of lowercase f on an interval I if the derivative of the antiderivative equals the function for all x in the interval. If capital F is an antiderivative of f on an interval I, then the most general antiderivative of little f on I is capital F of x plus c, where c is an arbitrary constant. And what does this all mean? This is saying if our function is x squared, then if we go backwards and instead of trying to find the derivative, we try and find the antiderivative, we might think that the answer would be 1/3 x cubed. Because the derivative of 1/3 x cubed would be x squared. And so we're just trying to go backwards. Now, I'm telling you that's wrong. And the reason I'm saying it's wrong is because you have to look at some other function, x cubed over 3 plus c. Well, its derivative is also x squared. That brings us to the next slide, which says that if you go and take the antiderivative of f of x equals x squared, you actually produce a family of antiderivatives. In other words, we get the antiderivative equals 1/3 x cubed plus some constant c. Find the most general antiderivative of each of the following functions. So you just want to ask yourself, what function's derivative is sine? Well, you know the derivative of cosine is a bad sign. So if we want to take the antiderivative, we better say negative cosine x. And don't forget plus c to get the general solution. B is a little bit tricky because it's asking us what is the function whose derivative is 1 over x. So you'll remember that the derivative of ln absolute value of x was equal to 1 over x. And I told you that it was very important that we had this ln of absolute value of x for a reason, and the reason is right here. When you want to go and take the antiderivative, you can't just say it equals ln x, because it only equals ln x plus c for values greater than 0. And it actually equals ln of the opposite of x, because we need the ln of absolute value of x plus c for values less than 0. And of course, if x equals 0, it's undefined. So just in general, how do we undo the power rule? We need to add 1 onto the power and divide by whatever we added. Because the derivative of this is going to be 1 over n plus 1 times n plus 1, which is 1, times x to the n plus 1 minus 1, which is just n. So the derivative of this is going to give us this, and then we can't forget our plus c. Here are some anti-differentiation formulas, and I don't really memorize these. I just memorize the derivatives and then I try and go backwards in my head. It gets too confusing if I try and memorize everything. So I do not memorize these at all. So now we want to find all functions g such that the derivative of g of x equals this. So before I go taking any antiderivative, just like I did when I was taking derivatives, I want to try and simplify things for myself. And this one looks like I can get rid of this quotient. So I have 4 sine x plus 2x to the fourth minus x to the 1/2 over x is just x to the negative 1/2. And so now I can take the antiderivative. Pull the constant out, and the antiderivative of sine is negative cosine. The antiderivative of this would be two times 1/5 x to the fifth minus, so what I tend to do is I just add 1 onto the exponent, so negative 1/2 plus 1 is 1/2, and then I just kind of do the reciprocal over there because I want to undo whatever I did, so when I multiply these two I get 1. And then I need my plus c. And that's the answer. Differential equations. We often need to find a function given knowledge about its derivative. An equation that involves the derivatives of a function is called a differential equation. The general solution of a differential equation involves an arbitrary constant or constants. But there may be extra problem conditions that will determine what these constants are. So what do I mean? In this example, they tell us what f prime is. They want us to find f of x, but they give us an initial condition. And we can use that initial condition to find our constant c. We have that f prime equals e to the x plus 20 over 1 plus x squared. And this will hopefully ring a bell. Remember, the derivative of arctan is 1 over 1 plus x squared. So when we go to take the antiderivative of e to the x is just e to the x plus 20 times arctan of x plus c, of course. And then we use our initial condition. We know f of 0 equals negative 2, which equals e to the 0 plus 20 arctan of 0 plus c. And so we have 1 plus 20. What is the angle whose tangent is 0? What is the angle whose y over x coordinate on the unit circle is 0? That's just 0. So we have minus 2 equals 1 plus c. C equals negative 3. So we're left with f of x equals e to the x plus 20 arctan of x minus 3. And that's our answer. And here's just a graph. So now we want to find f if f prime prime equals this, and I'm given 2 initial conditions. I'm just going to rewrite f prime prime. So the derivative is just going to be add 1 up there, and so then you divide by whatever I had. Add 1 up there and divide. And then just add on an x, and don't forget your plus c. And so f of x, I better simplify this. So I'm going to add 1 and divide, so 4 divided by 4 is just 1. Going to add 1 on there, and then divide, 3 divided by 3 is 1. Add 1 and divide, 4 divided by 2 is 2. Don't forget plus cx, because I need to take the derivative and still get my c. And then I need to add a constant. I'm just going to call it d for now, because I need to add my arbitrary constant. Now we have two initial conditions. We know f of 0 equals 2, and we know f of 1 equals 1. And so we're going to be left with 0 plus 0 minus 2 times 0 plus c times 0 plus d equals 2. In other words, d equals 2. And so now we can plug in our 1, and we get 1 plus 1 minus 2 times 1 plus c times 1, and we now know our d is 2. So we have 1 equals 2 minus 2 plus c plus 2. C equals negative 1. Therefore, f of x equals x to the fourth plus x cubed minus 2x squared plus cx, so we have minus x, plus d. In this question, we're asked to sketch the graph of the antiderivative that satisfies the initial condition f of negative 1 equals 0. So in order to sketch this, we are given the slopes. In other words, the fact that f of negative 1 equals 1 plus negative 1 cubed minus a minus 1, which would be 1 minus 1 plus 1. The fact that f of negative 1 equals 1 means that for all values of x equals negative 1, the slope of the tangent line equals 1. So we can go ahead and graph what we call direction fields. If I want to graph the antiderivative, and I know that f of negative 1 equals 1, then wherever x equals negative 1, I want to draw in a slope of 1. And don't forget, a slope of 1 is a 45-degree line, so I'll just draw in these little direction fields indicating that. So now I need to go back, and let's see what f of 0 is. Well, 1 plus 0 minus 0 equals 1. Yet again, at all x values is 0, I'm going to get a slope of 1. Let's go back and try to find it at 2 and at 3. It's going to be 9. The square root of 9 is 3. So I get 1. F of 3 is going to be 1 plus be about 2.292. And so, oops, I skipped f of 1. What was f of 1? It's about 0.414. So that's going to be like half as steep as my 45 degree. So I just draw them all in. Then we had f of 1 equals 1. And then we had f of 3 equals 2.292. And so that's, about twice as steep. So, these are just approximations. We kind of just draw in what's going on. And these are the easy kind because the derivative only depends on the x value here. And you'll see what I mean by that later. And we also knew that f of -1 equals 0. So we have a point, -1, 0. And so what we try and do is, remember, these are the slopes of our curve that we've drawn in. And so we just try and pick up the curve and see what's going on. We see that our slope was increasing, and then it kind of was increasing more. And so my thick line would be an approximate solution curve. I just picked up the slope fields and saw what was happening to my function. So this isn't exact, it's just an approximation of what the antiderivative looks like. So now we're just going to do a quick application to rectilinear motion. So remember, if we have an object moving in a straight line that has a position function s, then the velocity is just given by the derivative of the position function, meaning that we can now go backwards and get the position function from the velocity function. We can get the acceleration from the velocity function. And so if we have a particle moving in a straight line and it has an acceleration given by 6t plus 4, then the velocity is just the antiderivative of that. So you add 1 on here and divide. So 6 divided by 2 is 3 plus 4t plus c. They tell us that the initial velocity is -6 centimeters per second. So I'm just going to go ahead and plug it in right away so I can get my c value before I take another antiderivative. So now I know my velocity is 3t squared plus 4t minus 6. And so my position function, add 1 and divide, so t cubed, add 1 and divide, 2t squared minus 6t plus some other constant, I'm just going to call this c1, and this is c2. And so I know that s is 0 equals 9, so 0 plus 2 times 0 minus 6 times 0 plus c2 equals 9. In other words, c2 equals 9. So I have my position function t cubed minus 2t squared minus 6t plus 9. So that is my position function. Finally, we have a ball is thrown upward with a speed of 48 feet per second from the edge of a cliff 432 feet above the ground. What do we know? We have an upward speed of 48 feet per second. So the initial velocity is 48. And it started here, so our initial height was 432 feet. So how are we going to start? Well, since this is just dealing with gravity, we know that the acceleration is -32 feet per second squared. And so the velocity is just going to be -32t plus some constant. And so We knew that v of 0 was 48. In other words, C1 equals 48. So take another antiderivative, add 1 on. 32 divided by 2 is negative 16 plus 48t plus some constant. And you know the initial position was 432. In other words, C2 equals 432. And so we have S of t can be given by negative 16t squared plus 48t plus 432. So that's our answer to part A. Part B says, when does it reach its maximum height? Well, it reaches its max height when the derivative of the position function, in other words, the velocity, equals 0. And so when does that happen? So let's go ahead and look at our velocity function, which was negative 32t plus 48. And you know that equals 0 when t equals 3 halves, 1.5 seconds. And so let's just quickly make our sign chart to make sure it's a maximum. And so you know that this is a line that has a negative slope, so we would obviously go from plus to minus, indicating that we had a max there. So just to get you ready for how to write for the AP exam, we can say that t equals 1.5 seconds is a max because velocity changes from positive to negative at t equals 1.5. And so I'm going to tell you a lot more about how we have to write for the AP exam, but this is just preparing you. So part C says, when does it hit the ground? When does it hit the ground? It just hits the ground when the position equals 0. So this is nothing fancy. Set the position equal to 0. Might factor out a negative 16. And unfortunately, I can't factor that, so I'm just going to have to use a quadratic formula. Minus b plus or minus the square root of b squared minus 4ac all over 2a and of course my time can't be negative, and 3 minus 3 root 13 would have been negative, so we have to cross that one out. So it hits the ground after 3 plus 3 root 13 over 2 seconds. And that's it for this lesson.